Here we will be looking at Monte Carlo estimation as one way to compute integrals. We look at the problem of computing expectations, that means computing the value of the integral f of x times p of x dx. It turns out that expectations are pretty important and they appear in many places. For example, if we want to compute the moments of a random variable, we need to solve the integral of x to the power k times p of x, which is exactly the expected value of x to the power k with respect to p. Or if we want to compute the marginal likelihood, which is an important quantity for model comparison, then we need to compute the integral of the likelihood p of x given theta times p of theta d theta, where theta are model parameters and x are training data. We can therefore write the marginal likelihood also as the expected likelihood with respect to the parameter prior p of theta. A third place where expectations appear is when we make predictions in a Bayesian model. With the parameter posterior p of theta given x, the predictive distribution is the integral of p of x star given theta times this parameter posterior, which again can be written as the expected predictive distribution where the expectation is taken with respect to the parameter posterior. The key idea behind Monte Carlo estimation is to make use of random numbers to approximate the expectation. And here is how it works. We compute the expectation via statistical sampling. If we draw samples from p of x, we evaluate f at those samples, sum the function values up and divide by the number of samples. For example, if we were to make predictions in a supervised learning setting, such as Bayesian logistic regression with training set D and test input x star, we get the predictive distribution of the label y star by solving this integral problem. Since this integral cannot be computed analytically, we can use Monte Carlo estimation where we draw model parameters from the parameter posterior, and for each drawn model parameter, we make a prediction of the corresponding label. We sum them up and then divide by the number of samples. And this gives us the Monte Carlo estimator. Monte Carlo estimation has some nice properties. The estimator is unbiased and asymptotically consistent. That means if we sample long enough, the estimator tends to the true expected value plus an error term. And that error term is Gaussian and its variance shrinks linearly with the number of samples, independent of the dimensionality. Overall, Monte Carlo estimation gives us the right answer if we sample long enough. So far, so good. If we can draw samples, then computing the Monte Carlo estimator is fairly straightforward. But how do we get these samples? If p is a simple distribution, we can use libraries that do the job. Pretty much for any distribution that has a name, this works. For example, Gaussians or Poisson distributions, Dirichlet distributions, Laplace distributions, and so on. But if p is complicated, we need to use other methods. For example, rejection sampling or importance sampling in low and moderate dimensions. Or we can use Markov chain Monte Carlo methods that allow us to sample from unknown distributions. For an excellent overview of sampling methods, have a look at Ian Murray's NeurIPS tutorial from 2015. Now let's have a look at an example. Assume we want to compute the expected value of a function f of x, which is defined in this orange box and also drawn up here. This is the function we want to integrate from -3 to +3 with respect to a uniform distribution. We get a Monte Carlo estimator by sampling from the uniform distribution, evaluating the function at those samples, sum up the function values and divide by the number of samples. What we see here is that as a function of the number of samples, the estimation error goes down and so does the variance of the estimator. But if we remember back to numerical integration, we also realize that Monte Carlo estimation needs quite a few more function evaluations than numerical integration, where we could push the integration error down to 10 to the -3 with about 10 function evaluations, whereas the Monte Carlo estimator for this function needs about 100,000 samples. So this is the level 10 to the -3 here, so that's about 10 to the 5, 10 to the 6 many samples we need to get to this accuracy. Monte Carlo estimation has a range of different application areas. for example, anything that is related to empirical risk minimization, but it is also a key ingredient in reinforcement learning to compute expected long-term rewards, or in Bayesian optimization for integrating out hyperparameters or computing acquisition functions. It's also frequently used in variational deep learning and in probabilistic programming. For an excellent introduction to probabilistic programming, check out Frank Wood's NeurIPS tutorial from 2015. On the more practical side, Monte Carlo estimation is also frequently used in high-energy physics and robotics. There are a few things that we may want to consider when doing Monte Carlo estimation. Monte Carlo estimation requires many samples and function evaluations to get a good estimate of the value of the integral. That means two things. First, we must be able to generate many samples using computationally efficient and low variance samplers, ideally. Second, we must be able to evaluate the function many times. That means the function evaluations must be cheap. But Monte Carlo estimation is a very good method for learning if we're mostly interested in an unbiased estimator for an expected value. There are also some criticisms around Monte Carlo estimation. For example, the estimator does not take the location of the samples into account, which can be problematic especially in small sample regimes. To summarize, Monte Carlo estimation uses random numbers to compute expectations. The estimator has some nice properties and it scales to high dimensions. But the key difficulty is the question of how to generate samples. We didn't cover this here, but Ian Murray gave a great tutorial on this 5 years ago, which I can highly recommend.